in R. In R, it will use the randomizer and the PWR packages, or you can just open a spreadsheet and download the GPower program, which you maybe Mark or somebody can put a link to GPower. Sorry, I forgot to do that in the chat, and you can play along there. All right, so it starts pretty slow. Some of you will know all this, but it will quickly pick up and pace. So asking a question, or also if you have a question, just pop it in the chat and maybe somebody will interrupt me if I don't see it, but feel free to pop in questions as we go, because it's quite a long seminar, so you don't want to wait till the end to ask your question. So basically, we often talk a lot in consultations about what a person's research question is. And that's because a lot of people don't think in great detail about what their research question is. They have it in the back of their mind, but really, if you are a little bit vague about what your research question is, it's likely that when you design a study, you won't be able to answer any question, because all of them are too vague. So it's best to ask a very specific question, and then you can design your study to answer that. So the first thing to think about is, what is your study population? So say you're in medicine, your study population might be a group of people that have heart disease. So it might be the people that have heart disease post-COVID, because maybe you're not interested in what happened during COVID, because it's kind of a weird time, so that's the time. In space, you might be interested in Australia, or you might be interested internationally, or just rural areas, something like that. Clinically, medically, that would be the people with heart disease. So there are specific subset of the total population of everyone that you're actually interested in for your study population. So it's important to know who you want to know something about. So that's the study population. And then you need to know what your response is. So maybe you want to know heart attack, in the last 5 years, maybe that's your response, your outcome. And what are your predictors? So maybe level of exercise or diet predictors. That might be the things that you're interested in. So you might be interested in, how does the level of exercise impact the risk of heart disease among people with, impact the risk of heart attacks among people with heart disease in Australia in pre-COVID. And so that might be your research question that you're actually interested in. So it's important to be pretty specific about that. And then we can design a study to answer that question. So a lot of people get confused about what you actually get from a sample. So, so here I've got some people who either do or don't have allergies. So blue people have allergies, and green people don't. And so, so maybe we collect a sample of 4 people on the left here, and we find out that 2 of them have allergies and 2 of them don't. So what we know about this sample is that the sample proportion, which we'll call p hat here, is 0.5. So half of the people have allergies. But we're actually never interested in the sample. The sample is just a way for us to make inference about the population that we're interested in. And so we collected our sample from a population, and now we want to make inference. So what we want to make inference about is the true population prevalence of allergies. And when we have a sample like this of 2 people with and 2 people without, the inference we can make is that we're 95% confident that the proportion of people with allergies in the population is somewhere between 15 and 85%. So it could be that the population that this sample was taken from looks like this, with about 50-50 allergies, non-allergies, the same as our sample. But of course, we never know the population, so we only have the sample to infer the population. And so it's quite easily possible that actually 85% of people in the population have allergies. And that's still consistent with our sample. So we have the sample, but we never care about the sample. So reporting the sample statistic is never the thing that we're interested in. Always what we're interested in is the population. And there's always some uncertainty from our sample about what the population looks like. And we never get to know, and we only get to know up to the point of how much data we've collected from that population. Any questions at this point? All right, so what's this? The word population sometimes pops up in statistics, and it's worth just talking about what we mean by that in statistics. So it's not the same as a biological population, which might be like the population of Australia or the population of some species of animals. So in statistics, it's the collection of all possible observations. So it might be the same as a biological population. So you might be interested in all the people in Australia. That might be the population of interest, but it might not. It might just be a subsection of that population, or it might be nothing to do with people. Now, the population is the thing that we're always interested in, and characteristics of the population are called parameters. So, for example, the population proportion, like here on the right, that's the parameter that we are interested in estimating. We want to know the prevalence of allergies. But all we ever know is the sample, and the sample is just a collection of observations from the population that were observed. So we're able to see these ones. And characteristics of samples are called statistics. So this is where the word statistics kind of comes from. So a statistic is just a characteristic of a sample. So that would be p hat here. So half is the proportion. And it's important to note that the statistics of a sample will differ from the true population parameter. So it's never true that, you know, this is not the true proportion of allergies. This is just the sample proportion of allergies in your sample. And if you took a different sample, you would absolutely get a different proportion. Okay, just chuck in there with questions if you have them. This one is probably will require you to type something into the chat. So confounding. You might have heard the word confounding. It means that differences due to experimental treatments or predictors can't be separated from other factors that might be causing the observed differences. It's kind of a mouthful, so I like to use this example. So you go to a school and you get a sample of kids at the school and you measure their height and you measure their maths ability, you give them a maths test. And then you look at their height and their maths ability in your spreadsheet, and you see that taller children tend to be better at maths than shorter children. So what do you think is the confounding variable here? Is it true that taller children are better at maths than shorter children? Is height? Some people have, yeah, pop it in the chat. Yeah, so a few of you have said age, and that's absolutely right. So obviously older children are both taller and they have learned more maths because they're older. And so, so that is the confounding variable. And it's when we have a situation like this where we know what's going on, it's very easy to find a confounding variable. But usually we're doing research in areas where we don't really know what's going on. That's the point of research. So it's really hard to know what the confounding variable is here. Sorry, in general in research. So we can't always sort of tease out what the confounding variables is because we just don't know the relationships of all the things that we're interested in say, a person's body or in ecological communities or whatever. So we've got two options to remove the effects of confounding because we don't want to have confounding. We don't want to conclude that taller children are better at maths. We know if we control for age, we'll find that the height of children doesn't have anything to do with their maths ability. It's just that older. Two children that are the same age and different heights will tend to have the same maths ability on average. So to remove the effects of confounding, we've got two options. One is to conduct manipulative experiments, like clinical trials are the most common manipulative experiment done. This can completely remove the effects of confounding, and that you can use them to show causation. So you can say height is, taller children are better at maths, you would be able to say, if you conducted a manipulative experiment and found that that was true. In observational studies, where I'll talk about what these two things are a little bit later, you can control for confounding variables. However, for this to work, you have to be able to measure all possible confounders, which you can't do because you generally don't know what they are. So you can't show causation in observational studies unless you make a lot of assumptions. Okay, so I'll talk a little bit about manipulative experiments. Oh, Jan said not all tall children are older. This is very true, but on average they are. On average, taller children are older. So that's all you need. You need averages, not individuals. Okay, so manipulative experiments. So to conduct an experiment, you need controls, replication, and randomization. These are the three things that you have to have, and then you have a well-conducted experiment. So the first thing to think about are controls. So lots of things can influence the outcome of an experiment. It can be bad weather, floods, pandemics, basically anything that changes with the passage of time. Abir would like to know why we're doing manipulative experiments. If you want to be able to say that A causes B, some new drug is better than some other drug, or doing a lot of exercise is good for your heart. If you want to be able to say that anything causal, the only real way to do that is to do manipulative experiments. Does that answer your question? And yes, removing confounders is one of the things that happens when you do that. All right, so back to controls. So basically, if you recruit people to a study or collect samples for a study, and you watch them over time, they'll change. Like people, if you recruit some people that have depression, on average, the depression might go down over time, even if you didn't do anything. And if you also gave those people some counseling, maybe the depression goes down over time, but you need to be able to tell what would have happened if you hadn't given them counseling. So you have to always have a control to be able to compare your treatment to, so that you know what would happen without the treatment. Otherwise, it could be anything that changed over that period that caused the change that you observed in the sample. So that's the controls. Replication, you have to have replication so that you can attribute differences between treatment and control to the treatment, rather than the innate differences between subjects. So this will make sense in a minute. And then randomization is really allows you to overcome confounding when measuring the treatment effect. This is because regardless of any confounders, the probability of being in the treatment group is equal for all participants. So that's how you can remove confounding in manipulative experiments. Okay, so what about controls? Controls are really common and should always be there if you can have one. So for example, in a medical study, you might have subjects receiving a placebo, like a sugar pill in a clinical trial, or usual treatment if it doesn't involve medication. If you use cell lines, then unmodified cell lines would be a control. If in oncology, for example, then sites without any treatment applied might be the control that you're looking for. So you just want to know what would happen, what's going to happen if you didn't have the treatment that you're interested in, or the thing that you're interested in. And it's important to note that they should be as similar as possible to the treatment in every way except for the treatment. So this is why we do placebo, like sugar pills, because even giving somebody a medication has a measurable effect on their health. And so we don't want to attribute the placebo effect to our medication that the active medication that we're giving people, we want to tease out the proportion of it that is just because people are getting medication and the proportion of it that they're getting from the right or the medication that you're interested in. And it's really good in general to also blind everybody that can be blinded. So blinding means that they don't know, people don't know the allocation of the treatment. So the patient preferably wouldn't know, the treating physician. These are in medical studies, but in general, researchers, if there's a way for you not to know what the treatment allocation is, that's better for your experiment. Okay, dependence is another aspect of experiments that are important to think about. So most simple statistical methods assume independence, and independence means that independence between experimental units means that if you know the value of one, it doesn't tell you anything about the value of another one. So if you've got two people in your sample, knowing the heart rate of one person doesn't tell you anything about the heart rate of another person. So ways to break independence, ways to have dependent data, for example, is if you take measurements from the same person, they'll be more similar than measurements from different people. So they are dependent. Also, like measurements from the same hospital, so clustering, they're more similar than from different hospitals. It happens in many ways in space and time. So measurements from areas close to one another are more similar than measurements taken further apart. This is really important to think about. So you need independence generally for simple statistical methods. More complex statistical methods can take into account dependence, but it has to be taken into account. And then the last little, so Jan says measurements from the same school, absolutely, those would be dependent. So, yes, so yeah, so independence, and then replication I've just popped in here at the end because it's the easiest one. It just means you have to repeat the treatment to multiple subjects or samples. Abir says, how can measurements from the same school be similar? Because they are so, students from the same school will have the same teacher, might be a really good teacher, so they tend to have better marks than students from a different school, and so they're more similar. Yeah, exactly. Okay, so this is my new attempt at trying to get at dependence and replication pictorially. You can let me know if it works. So the first one, so we've got treatment and control. Now blue is treatment and cream is control. So here we've got no replication. So we've got one person in a treatment, one in control. This is a little hospital. And so you find that there are differences in blood pressure between this person and that person. Maybe you even measure them multiple times and you find that there's differences in blood pressure. So those would not be, you can't attribute those differences to the treatment because they're two different people. So of course they're going to have differences in their blood pressure due to any number of things, not just the treatment. So there's no attribution possible, and so there's no replication here. That's why that's not a good study design. Now, if you only have one hospital to work with, you're going to need to replicate the treatment to patients. So you have a bunch of patients in a treatment group and a bunch of patients in the control group. So here you have replication, that's good. However, you're sampling from the population of one hospital. So you're only going to be able to make inference about that population. You're going to be able to say, well, you know, there's a treatment difference, but it may not, that may not be the same in other hospitals because you've only sampled in one. But nevertheless, this is a perfectly good experimental design to look for treatment differences, as long as you understand the limitations. Okay, so maybe you have access to multiple sites. So then you could have a couple of hospitals, and you give everybody the treatment in this hospital, everybody the control here. So you do, it looks like you have replication because you have multiple people with treatments here with control, and you have multiple people with treatments. And if you put that in a spreadsheet, it would look like you have some good data. Unfortunately, there's no true replication because one hospital might be different from another hospital, and you can't untangle the difference between the hospitals from the difference between treatment and control. So this is not an appropriate design because there's no true replication here. So you've got a couple of options if you want to do that. So you can give some people the treatment in each cluster and some the control. And that's a good, so you still have dependence within hospital, but if you take that into account, that's perfectly fine and then you can still compare the control and the treatment to each other and get a valid estimate of the differences. So that's good. Another way to go is if you can't, if the treatment that you want to apply can't be applied within the cluster, it can only be applied to the whole cluster, then you're going to need to have multiple clusters that have the treatment and multiple clusters that have the control. And you still have dependence and replication here, but in a different way. Any questions about that? Oh, I have some positive enforcement. Are there 8 different locations in the last? Yes, there's 8 different hospitals here, and 4 of them have been given, like all the patients in there have been given the treatment, and in 4 of them, all the patients have been given the control. All right, so that's manipulative experiments. So when you get to go somewhere and manipulate the environment, what about when you have observational data? You looked at records from hospital, or you have a look at some species and how what kind of temperatures they occur in. So you have observational studies because you're not imposing any treatment, and you're definitely not randomizing who the treatment is given to or what the treatment is applied to. So you have an observational study. They can't give you the same level of evidence as manipulative experiments and can't prove causation, but they're often the only available thing for a couple of reasons. Sometimes it's ethics, so we can't just randomize people to smoke, for example. Observational studies are a lot cheaper. And sometimes you can't really do experiments, in particular when you have rare outcomes. So it's not really possible to do an experiment because the outcome might never happen in either group. And even when these are not the case, observational studies are a really efficient way to generate hypotheses that you can later test with manipulative experiments. So people do a lot of observational studies. There's a couple of types, and some of them are better than others. So cross-sectional means that you go out and you collect data at one time point for both the exposure and the treatment. So in medicine, this is, for example, if you're interested in how the association of smoking and heart disease, you go out and you collect data on patients and you ask them if they smoke and you ask them if they have heart disease, or you look at their records and see if they have a heart disease. So both the exposure and the treatment, both the exposure and the outcome happen at the same time. You ask the question at the same time point. They're really fast and cheap and good for hypothesis generation, but obviously they have many bias problems, because if you smoke now, it doesn't mean you smoked before, and smoking won't immediately cause heart disease. So there's a time lag. There's also lots of confounding that happens. So they're good for some things, but they're not the best kind of observational study. Case control studies, which are retrospective, are a good way to investigate rare outcomes. So if you have a rare outcome, you might look at some patients that have this rare outcome, like a rare disease, and then you might match them to some healthy patients that don't have the disease. but are similar in every other way. So they have age and sex and similar attributes, and see what the differences are between the patients with the disease and without, to try to see if you can tease out some associations for this disease. So they're good for rare outcomes, but bad for rare exposures. And a lot of bias can occur, in particular because it's hard to identify good controls. And then there's cohort studies, which are great. You can have prospective and retrospective ones, and basically you recruit people and then you follow them over time. And so in this kind of study, this is the best evidence of observational studies, because you have a temporal aspect. You can see, oh, they smoked for a while and then later on they got heart disease. So there's better evidence to see if there's a cause. Obviously, they're very expensive and time consuming, and there's issues like loss to follow-up. People stop picking up their phones, and then changes in exposure. So you might smoke for a while and then you don't smoke, then start up again, and so it's hard to know how to include that in your study. So observational studies are a good way to show associations between variables. So if you want to make a statement like smoking is associated with high risk of lung cancer, they're good for that. But often they are conducted when what we'd rather do is a manipulative experiment, like a randomized clinical trial. And so, but you can't do that due to cost or some other reason. For these kinds of observational studies, what you'd really like to do is estimate a causal effect, something like smoking leads to higher risk of lung cancer. So that's what you'd really want to be able to do. And that's very different from smoking is associated with a high risk of lung cancer. And so if you want to do that kind of thing, what you're interested in is a causal analysis. Keep in mind, so basically, without a manipulative experiment, you can never show causation without making some assumptions that you cannot test. So if you want to do a causal analysis, you'll have to make some assumptions about your data that are not possible to test. However, there are a number of tools that can make, that are able to sort of account for many of the biases in observational data. And these tools and statistics are called Causal Inference. They include things like target trials, DAGs, instrumental variables, inverse probability weighting, things like this. So if you're really interested in a causal link between two things and all you have is observational data, I would suggest you have a look at these things. Make sure you always clearly list the assumptions that you're making in your manuscript, because you will have to make some assumptions. And then the other thing is causal inference is quite hard to do. I'll give you a link at the end, even for statisticians, so you should get some advice. So it's not an easy thing to get to answer causal type questions from observational data. Okay. So randomization. So I think we're going to do something a little bit active. So if you've downloaded GPower in Excel, or if you wanted to do it in R, now's the time to open these things. So we said earlier that independence of subjects can be guaranteed by random sampling in manipulative experiments. And confounding of the treatment effect can be eliminated with random allocation of treatments to subjects. So we'll learn how to randomly allocate subjects to treatments, which is the most common thing that we have to do, most common randomization we have to do. And I'll show you how to do it in R and Excel. So in R, you'll need the randomizer package. So install it and then do the library. And it's relatively easy. So to randomize 12 subjects to 3 treatment groups, I've got 3 treatment groups, I've just called them A, B, and C, very boringly. We can use the complete RA function, so complete random assignment, and is 12. The conditions are A, B, and C. And I'm going to save the results in a variable called Z. Oh, want to show the last slide again. So you'll need to install the randomizer package and then call it in R, as usual when you just when you have a new package that you want to use. It's randomize ZR. There's no E. Yeah, so complete I. So yeah, Mark's got it. So I've saved that in a variable called Z. So if I want to have a look at if I've done the right thing, I can do table of Z, and that will tell me how many are in each treatment. And I can see now that there are 4 in each treatment, which is good. That's what I wanted. And then if I want to know which treatment each patient is allocated to, I can have a look at the first numbers in Z. So the first patient's allocated to treatment C, the second one to A, the third one to B, and so on. So this is my random allocation. So it's pretty straightforward. You can also do it in, oh, sorry, yeah. So if you wanted to do something a little bit more complicated, it's also quite easy. So say you wanted to randomize 100 subjects, but you wanted 60 in the treatment group and 40 in the control group, then you can use this M each variable. So you just tell it how many, so there'll be 60 in the treatment group and 40 in the control group. And again, we have a look at the table Z, and that tells us that we've done the right thing. So we've got 60 there and 40 there. And then if we look at the first 10 patients, we can see that the first 2 are in the treatment group, and then there's 1 in the control, and so on. So pretty straightforward. If you want to do it in Excel, it's actually really easy as well. So all I'm going to do is I'm going to have a column for subject. So I will do 1, 2, and then hopefully you know how to autofill. To autofill, you can just highlight these 2, and then you can pull down from the corner. I want 12 subjects. So I've got that. And then to do the allocation, so this is treatment. I want A, B, and C, right? So I'm going to write A, B, and C in the first 3. And then I'm going to just highlight this. If I double click, this will just fill all the way to the bottom. And you can see what's happened is I've got 4 A's and 4 B's and 4 C's, which is what I want, but I don't want them to be in this order. But I have the right number of each treatment. And then I'm going to use the random function in Excel to, hopefully you can see this. Can you see this? Can you see my Excel slide?
Yeah.
Great. So all I need to do is go equals rand, open bracket, close bracket. So the equals is important. That tells Excel it's a function. So I'm going to do that. That will give me 1 random number, and then I'll just highlight it and double click so that it fills all the way down, or you can pull down to fill it. And now I've got a bunch of random numbers, and that will help me do the random allocation. So what I'm going to do now is I'm going to select these 2 columns, but not the first one, and then go to editing, sort and filter, and custom sort. And then you just need to sort by random. And once you do that, it'll sort the treatments in a random order, which doesn't look very random for this one, but interestingly. And then you've got your random allocation of treatments to subjects. Now I'm just going to delete this, this random column, and we're done. So I can see the first 2 subjects will be in group B, then they'll be in 1 in C, 1 in A, 3 in C, and so on. Yeah, so sorry, didn't catch the content of the slide. You don't need the slide, you just need the, can you please, the last step, what was the last step? I think the last step was, so I select the treatment and random column, and then, yeah, oh, I see, you want to see the slide because it spells out the steps. Maybe I'll just I'll just continue, and maybe I'll show you again at the end. Yeah, I think I'll just continue and I'll show you again at the end. So yeah, the steps are in here, and I'll let you have a look at the end what they are. Okay. Okay, so can we do it in Excel for e.g. 40 and 60? Yes, you can. I didn't do that as an example, but it's pretty easy. So if you wanted to do an unequal allocation, say you wanted 2/3 to be in A and 1/3 in B, or I guess you wanted, so say I wanted 2/3 in A and 1/3 in B, then I want to be able to have a ratio of 2 to 1. So I just need to make sure that initially I have a ratio of 2 to 1. And then when I fill it, it'll have a ratio of 2 to 1. And then I just do exactly the same thing. So that was Abir's question. I'm happy to do that again at the end if you want to stick around. All right, so that's randomization. It's really pretty easy to do randomization. So there's not really any technical reason not to. When you're doing your own experiment, if you are able to do a manipulative experiment and randomize the treatments, it's not hard to do. So we are also very happy to help you with randomization if you need something more complicated. All right, so what about sample size? So once you have an experimental design, you know, that has everything that you need, the controls, replication, independence, all of that, you still need to decide on how many subjects that you need. And this is a tricky thing because it depends on the population, and we don't know the population. So we have to make guesses about the population, and then educated guesses about the population, and then work out a sample size that's going to be able to give us the answer in that guessed population. Okay, so the things we need to make guesses about are effect size and variation. So first of all, the aim of a study is to detect an effect if one is present. So detect the difference between two groups if there is a difference. That's what we want to do when we do an experiment. If you fail to do so, that's called type 2 error or false negative. So you don't want that. If there is an effect and it's of a size that makes a difference that's meaningful, then you want to be able to detect that. So you don't want to have a sample size that's too small to detect the effect that you're interested in. And say you have a 5% chance of detecting the effect, then there's no point at all in running the study. So if we have some information about the effect size and variability, then we can conduct a power analysis, a sample size analysis before we start the experiment to make sure that our sample is sufficient. Now, the best way to estimate variability is to conduct a pilot study. This is like the ideal situation. Most of the time, you don't have a pilot study. But somebody else may have conducted a similar study and published their results, and you can go to that and use that as a way to estimate variability in your data, sorry, in your population. What about effect size? What's this effect size business? There's lots of definitions of effect sizes, and I guess I'm using the term pretty loosely. But this is the magnitude of the effect that you're hoping to detect. So say you have two samples, a treatment and a control, then the effect size is just the difference between the means, the population means of your two populations, a population that receives treatment and a population that doesn't receive treatment. Obviously, this is the thing that you're trying to estimate when you are collected. This is the point of your study, is to estimate this treatment effect. So you're not going to know what it is because we haven't done the study yet. So we don't know what it is. So the best way to choose an effect size for your sample size is to consider what effect size is actually meaningful, either clinically or biologically. So, if your response is blood pressure, what differences in blood pressure are going to actually be meaningful for this treatment to be relevant medically to these people, like for people actually to be prescribed the treatment that you're interested in. So that should be the effect size that you use for the sample size analysis. Another common way to get an effect size is to look at the previous literature for what their effect size was. You can do this to get an idea, but it often results in an effect size that's below what we would consider relevant, because what they got in their sample is still just an estimate. It's not the true population value, and they may have had a small sample, so they may have estimated the true effect size poorly. And so at least have a look at their confidence interval to see what sort of effect sizes are plausible before you use an effect size from previous literature. Okay, so if we want to actually do a sample size, Ma said literature often reports exaggerated values due to publication bias. That's an excellent point. Yes, so the small effect sizes won't have gotten published. That's very true. Okay, so you need these things. You need an estimate of variability, usually a standard deviation. If you have a standard error, you can calculate a standard deviation from that, but they are not the same thing. You need an effect size. So we think about what is clinically meaningful or biologically meaningful. Then there's a typo. You need a significance level. So this is, if you're conducting a study, you might think, oh, I'm going to say something is significant if the p-value is 0.05. Usually we use 0.05 for historical reasons. And then you need power. Power is the probability of declaring significance. So it's like, if you conduct this experiment with the sample size that you're eventually going to get from this analysis, how likely are you to be able to detect the effect, to get a significant results from the experiment? So you have to set that. It might be usually the usual things that people use, especially for ethics, are either 80 or 90%. So 0.8 or 0.9. I would suggest 0.9, but I've used 0.8 in the examples. So what does this mean? It means that if I set up my power to 80%, it means that I want to be 80% certain that I'm going to be able to detect an effect of the size that I've specified. Do you mind explaining power again? I don't mind at all. So power is just a term in statistics, and it means how likely are you to get a significant result when there is an effect in the population. So the population you have, say there is an effect. How likely are you to, when you collect your sample and do your statistics, find a significant p-value? So that's the definition of power. That kind of you can think of it different ways, but that's probably most useful in this context. So dependent on sample, absolutely dependent. No, so the power itself is, you do that ahead of the sample size. So you want the sample size you get will depend on the power you choose. So if you choose power of 0.8, that means the sample size might be 20. But if you choose the power of 0.9, that means you want to be more certain that you're going to get a significant result. So the sample size you're going to get out will be bigger, because you will need a bigger result to be more certain. Okay, so here is a sample size analysis for a 2-sample t-test, just because it's the most commonly used. Please remind me where beta comes from. Don't worry about beta. It's not important. Okay, so 2-sample t-test. Basically, it's just you've collected data on some subjects in 2 groups. So one has one treatment and one has another treatment, or it doesn't have to be a treatment. And they're all independent from each other. So each subject is completely independent from every subject in either group. It is type 2 error, yes. most of you will be familiar with that t-test, but that's basically what you would do. If you have two groups of subjects, you want to see if they're different on average. So Alice is interested in how diet affects weight gain. So she feeds a high-fat diet to mice in one group and a high-carb diet to the other group. And both diets are controlled to have the same calorie content. And so she wants to know what sample size she's going to need. So she knows from literature that the standard deviation of weight gain for both diets is about 0.9 grams, and that the difference between groups in other previous studies has been around 1.3 grams in the literature. She wants to know if there's a difference of 0.5 grams or more between the average weight gain between diets. So she wants to know what sample size she's going to need. So how are we going to do that? Well, we can use the power package, PWR, in R, and we'll also use GPower to do it. So what you do in power, it has a bunch of values, and the one that you're interested in, you just leave it as null. So we're interested in the sample size most of the time. So we're going to leave n as null. So I'll show you how that looks. So you can see down here in the t-test example, I'm going to leave n as null. But we do have to specify all the other things. So we need d, we need significance level, and we need power. Now, significance level and power are easy. Significance level is always 0.05 for a sample size analysis. And so for no, just like I said, historical reasons. Power might be 0.8 or 0.9, depending on how sure you want to be. Often ethics applications these days would like 0.9 actually. And then the important thing that you do need to calculate is this D. D is a standardized effect size, a Cohen's D in this case. And for us, it's just going to be what I've been calling the treatment effect divided by the standard deviation. So we remember we need the effect size, this treatment effect, and we need the standard deviation. And so the treatment effect that Alice is interested in is, let's have a look. She wants to know if there's a difference of 0.5 grams or more. So she's looked at the literature and found that it's 1.3 grams usually, but she's actually interested in smaller effect sizes than that. So, so she's interested in 0.5 grams. And the standard deviation she's found in the literature is 0.9. So if we just pop that in the equation and we get a, oh, I didn't print it. Didn't print. Well, that's silly. If it printed, let me just open it so I can show you. How are we doing for time? Ooh, we're almost done. Wow, I'm nowhere near finished. Okay, let me just do this real quick. Can I do want to show you how it looks. So I'm going to do library. I'll do it up here. I'll do library. Oopsie daisies. PWR. And then I will do treatment effect like that. And so treatment effect. And then sigma. And then if I do this, I get this output down here, which tells me that n is 51.8. So I have to round up because I can't have 51.8 mice, so I need 52. And it says that n is the number in each group, so I need 52 in each group. And that's if I want to have an 80% chance of detecting the population difference of 0.5 or more using the 2-sample t-test. So, so that's basically it. It's very straightforward. In G-Power, it's also pretty easy. So I'll bring up G-Power. So let's go through this a little bit. So I need to go to t-tests here and choose means difference between two independent means, two groups. So that's the one. And then we want a priori. And for some reason, the tails is always set to 1 by default, which is terrible. It should be 2. And then we want, what's the power that we want? We decided we want 0.8. So I'll change that. Alpha is right, so it's 0.05, so that's good. So now I just need to calculate the effect size. And to do that, I can use this, oh geez, sorry. Whenever I go to the top of the screen, the little thing pops down. That, okay. I can use this determine little box. And if I go n1 equals n2, what I do is I'm just going to leave the mean of group 1 as 0. It doesn't actually matter. What matters is the difference between them. So in the difference, I will put 0.5, and then standard deviation of each group, I will put 0.9. So I've got here 0.5 and here 0.9. And then I'll do calculate and transfer to the main window, and that will fill in this effect size, this Cohen's D. And then I can just calculate and I get the same answer. It already rounds it for me. So I got 52 in each group. So that's how you do that. Okay, so I'll just go through the last bit without showing you the examples. So Utama would like to know, don't we need the population size in here to determine the sample size? Generally, we assume the population is infinite. It doesn't really matter if it's big enough. If you have a small total population, then in some cases it matters. But yeah, generally the population size is not something we worry about. So for proportions, sometimes the total population is something that you put in. Okay, so this is the bit where I tell you how to get away with having a smaller sample size. So I'm sorry that that's the bit that's gone over time. I'll probably just keep going for another 5 minutes if that's okay. So what you want to do is blocking or stratification. They're kind of interchangeably used, and I couldn't work out what is actually a definition of either of them. So I'm just going to go with either. So basically, if you randomly allocate experimental units, this can lead to high levels of variation between units, which makes it harder to detect the effects that you're interested in. And if you group them into blocks with similar attributes, for example, location, time, treating doctor, age, that can explain some of the variation. And that can allow us to have more precise estimates of the parameters of interest and have more power, and so smaller sample sizes. Sometimes blocking is unavoidable. So for example, when sampling patients in hospitals, then a hospital is going to be a natural blocking factor. If you sample species at a particular location, that location is going to be a blocking factor, so you can't avoid it. But sometimes it is avoidable, but sometimes it's good to do it anyway. So that's what we're going to talk about here. So the way to increase power with blocking is to allocate treatments within blocks. So for example, some patients within each hospital get each of the treatments. So that's not always possible, but it's desirable. It's a good thing to do when you can. You have to make sure that you take blocking or stratification into account when you do the analysis. That's important. So that's they're cause dependence, and dependence needs to be taken into account. Other blocking examples include, say, case control study designs where they're a type of blocking, or an individual can be a blocking factor, so a person or a mouse. So sometimes we can sequentially apply all treatments to each individual, or sometimes we can take a measurement before and after treatment for each individual, and that gives us a natural blocking. So change from baseline is a very good way to do blocking, and very efficient in terms of power. It can have a huge effect on power. So I've recalculated here the sample size required for Alice's experiment, but so the change I've made is, instead of having mice in each group, I've just given each mouse both diets with a washout period in between and measured their weight gain. And so to do that, we need an extra piece of information, and that is the correlation of weight gain for a mouse over time. And Alice manages to find that in the literature, which is about 0.7 for her. So if I have that little extra piece of information, I can use R, for example, to do that. The code is a little bit slightly harder because you have to do this bit. I've just done it for you. You just do it every time. All you have to do is specify the correlation. Again, the treatment effect is the same, 0.5 as before. Sigma is the same, 0.9. And this will work out the standard deviation of the differences. Because when we have paired data like this, we want to use a paired t-test. And a paired t-test is actually just a t-test on the differences. So it's the standard deviation of the differences over time for each mouse, or differences between treatments for each mouse, that are actually relevant. So once we have that, we just plug it into the same function. We need to do type equals paired here, but it's not really any more difficult. And we find that in this case, N is 17.2. So 18 mice are required for this experiment. So before we had 104, so 52 in each group. And now we have 18 mice total. We do have to apply the treatment twice to each mouse, but that's 18 is still much less than half of 104. So it's we get a substantial improvement in the sample size required by blocking like this. So it's usually very good to do. This will tell you how to do it in GPower. You just need to add the correlation. It's very easy. So whenever you can, so the easy blocking wins are whenever you can apply the different treatments within blocks, not across blocks, and take before and after measurements, so baseline measurements if you can. And what about more complex analyses? If you say you're not doing a t-test, most people are not doing a t-test. Well, a lot of people are not doing a t-test. You might be doing ANOVA or MANOVA or regression or some other thing. How do you estimate a sample size? For relatively simple things like ANOVA, you can still use GPower. You can definitely use R. You can often simplify your question, your main question of interest, to be approximately answered by a t-test or ANOVA. And that was, since sample size is always a guess anyway at a lot of things, it'll probably give you a reasonable idea of the sample size that you need. So I often do that. For more complex analysis, you might have to ask a statistician. Also, Mark from Stat Central runs a sample size course around February each year. So that might be worth doing. Abir asks a side question. Is it true that we shouldn't use t-tests for large samples? I've never heard that. That is not true. Okay, and then there's just some references for you, so you can follow up on some of these things. All right, well, thank you very much. Any more questions? Let me know.
Thanks a lot, Gordana, for the Excellent talk. Thanks everyone for sticking around. Just a reminder, if you haven't seen in the chat, a few people asked if this would be recorded. Yes, it is being recorded, and in the next couple of days, it will appear, a link to that recording will appear like on our website. So if you didn't see the link in the chat, just search for Stat Central and you'll find it.
Doesn't look like there's any other questions. Thanks, everyone.
Thanks.